Now here we are going to discuss Cauchy sequence. Now let us plot the sequences x n to be 1 by n and x n to be minus 1 to the power n 1 by n. So few of the terms, if I want to mention, it would be 1, 1/2, 1/3, 1/4 and so on and so forth. Here it would be minus 1, half, 1 by 3 minus 1 by 4, and so on and so forth. Okay? And then if I want to plot these sequences, you can see some very beautiful patterns. What is that? So the first point, suppose this is 0. So let us take, this is along n and these are the real numbers of the sequence. If this is 1, at 1 it takes the value 1. So let us take this to be 1, then this is 1. At 2 it takes the value half, this is half. At 3, this is 2, this is 3, it takes the value 1 by 3, 1/3. At 4 it will take the value 4, and so you can see the sequence is somehow going like this. Similarly, if I want to plot this, the first one is minus 1, this is minus 1, the first point is minus 1, the second point is half, that is this one. The third point is minus 1 by 3. So it will be somewhere there. The fourth point is 1 by 4, this is same as this, and something like this. Then you can see this prompts us to define a particular type of Cauchy sequence or a particular type of sequence that we are going to call Cauchy sequence. Okay? How we define this sequence? A sequence x n is called a Cauchy sequence in R if for each epsilon greater than 0 there exists an n greater than 0 such that x n minus x m is less than equal to epsilon for all m and n greater than equal to n. This time we are not talking about a limit, we are talking about two terms, two elements of the or two members of the Cauchy sequence, the nth element and the mth element. If x n minus x m their difference is less than equal to epsilon, whenever this m and n are greater than some capital N, that capital N comes up because we take some epsilon. If something like that happens, then we say that x n is a Cauchy sequence. Some examples let us take. every convergent sequence in R is a Cauchy sequence. Every convergent sequence in R is a Cauchy sequence. How this can be proved? Let x n converges to x in R, then given epsilon greater than 0, there exists capital N greater than 0 such that x n minus x is less than epsilon by 2 for all n greater than equal to capital N. Now, this is true for some m also which is greater than equal to n, that is x m minus x is less than epsilon by 2 for all m greater than equal to n also. Therefore, if I take x n minus x m, that will be, by the triangular inequality I can directly write that this is less than this plus x m minus x, and that is less than epsilon by 2 plus epsilon by 2, that is epsilon for all m and n greater than equal to n, and this is the definition of the Cauchy sequence, and therefore, every convergent sequence in R is a Cauchy sequence. Take another example. Let a n be defined as a 1 equal to 1 and a n plus 1 equal to 1 plus 1 by a n. This is called a recursive relation of a sequence, that is the representation of the sequence is done recursively. Then a n is a Cauchy sequence. Then a n is a Cauchy sequence. Now, a n is greater than 1. We know we can observe this. A n is 1 plus 1 by a n minus 1. Therefore, if I take the LCM, this turns out to be n minus 1 plus 1. This implies a n dot a n minus 1 is equal to a n minus 1 plus 1, and which is greater than 2, because a n minus 1 is also greater than 1. And then 1 by a n into a n minus 1 is less than half, reversing the order. Consider now a n plus 1 minus a n is equal to 1 plus 1 by a n minus 1 minus 1 by a n minus 1, right, and this is equal to a n minus 1 minus a n divided by a n into a n minus 1, and that is less than equal to half by this earlier property a n minus 1 absolute value. Now, similarly a n minus 1 is less than equal to half, is less than equal to a n minus 1, a n minus 2, etc. Then combining combining all these terms, we get finally a n plus 1 minus a n is less than equal to 1 by 2 to the power n minus 1 into a 2 minus a 1, and this is for all n greater than equal to 2. Hence, a n minus a m, this is the requirement for the Cauchy sequence, that is less than equal to a m minus a m minus 1 plus a m minus 1 minus a m minus 2 plus and so on and so forth. Finally, we are going to get n plus 1 minus a n, that is less than equal to a 2 minus a 1 into 1 by 2 to the power n minus 1, and that is multiplied with, I am taking the common, 1 plus half plus 1 by 2 square, so and so forth. We get 1 by 2 to the power n minus 1, and from here what we get, a 2 minus a 1 absolute value into 1 by 2 to the power n minus 1 into 1 minus 1 by 2 to the power n minus 1, 1 minus half. This is a GP, therefore, we get the sum of the GP, and that is less than equal to a 2 minus a 1 divided by 2, 1 divided by 2 to the power n minus 1, and that is less than a 2 minus a 1 absolute value divided by 2 to the power n. And this is why, because 1 by 2 to the power n is less than 1 by n, therefore, given epsilon greater than 0, there exists a capital N greater than 0 by Archimedean property principle, Archimedean property 2 into a 2 minus a 1 divided by epsilon should be less than this capital N, and this implies a n minus a m is less than epsilon for all n greater than equal to this n, and this completes the assertion. And this example leads to a general result which we shall discuss in the last module of this unit. Now, we have another theorem that says that every Cauchy sequence is bounded. The proof goes as follows: let x n be a Cauchy sequence, thus given epsilon greater than 0, there exists capital N greater than 0, such that x n minus x m less than epsilon for all n and m greater than equal to n. take in particular, this is in line with our result that every convergence sequence is bounded. So, we are taking a similar line of arguments. Take in particular epsilon equal to 1, then there exists some n naught greater than 0 such that x n minus x m is less than 1 for all n m greater than equal to n naught. Take in particular m to be n naught, then what we will get? Mod of x n is less than x n minus x m plus x m, but here we have x n minus x m plus x m. This is less than 1, the first term, and the second one is less than or equal to x n, and this is true for all n greater than equal to n. Now, take m to be maximum of x 1 mod, x 2 mod, and so on and so forth, x n minus 1 mod, n 1 plus this term. Then your x n is definitely less than equal to m for all n in the set of natural numbers, and this implies this Cauchy sequence x n is bounded. This completes the proof. The next theorem is the sum and the product of two Cauchy sequences is again a Cauchy sequence, right. How to prove this result? Let x n and y n be two Cauchy sequences. Take z n to be x n plus y n and w n to be x n dot y n. We estimate z n minus z m and w n minus w m based on the properties of the Cauchy sequences of x n and y n. Now, what is z n minus z m? This is x n plus y n minus x m minus y m, and therefore, this can be by the triangular inequality, this can be written as x n minus x m plus y n minus y m. Since x n and y n are Cauchy sequence, given epsilon greater than 0, there exist n 1 and n 2 greater than 0 such that x n minus x m less than epsilon for all n greater than equal to n 1, y n minus y m less than epsilon for all n greater than equal to n 2. We are using this result, we are using this property for this sum of the two Cauchy sequences. Let n to be the maximum of n1, n2, such that xn minus x m is less than epsilon and xn minus, I can take this to be epsilon by 2, so that it becomes, finally we end up with getting simply epsilon and yn minus ym less than epsilon by 2 for all n m greater than equal to this capital N. So, both the conditions will be satisfied when I take n to be the maximum of n1 and n2. And then Zn minus Zm would be less than xn minus xm plus yn minus ym. This is less than epsilon by 2, for all n and m greater than equal to n. This is epsilon for all n m greater than equal to n. Okay. So, therefore, Zn is a Cauchy sequence. Zn is a Cauchy sequence. Next, for the product, we have Wn minus Wm, and that is xn yn minus xm ym, and I can add some extra terms here, xn yn minus xn ym plus xn ym minus xm ym, so that this becomes xn yn minus ym. I can use in one step itself these things, xn minus xm. Okay. Now, since every Cauchy sequence is bounded, we have m1 and m2 real numbers, such that m1 is also greater than equal to 0, m2 is also greater than equal to 0, such that mod of xn is less than m1 and mod of ym is less than m2. Now, since xn and yn are Cauchy sequences, given epsilon greater than 0, there exist capital 1 and capital N2, capital N1 and capital N2 in the set of natural numbers, such that xn minus xm is less than epsilon by 2m and yn minus ym is less than epsilon by 2m, where this m is the maximum of m1 and m2. Then this Wn minus Wm would be, you can see, less than mod of xn, mod of yn minus mod of xn, mod of yn minus ym plus mod of yn ym. into mod of x n minus x m. I can apply these properties. Here this will be less than m, because x n is bounded by m 1 and m is greater than m 1. Therefore, I can immediately write m instead of this, and it is multiplied with epsilon by 2 m plus again m into epsilon by 2 m for all n and m greater than equal to n, where n is the maximum of n 1 and n 2, and this gives me less than epsilon for all n m greater than equal to n, and thus we have W n is a Cauchy sequence. This completes the proof. Now, let me deal with this problem. If x n is a Cauchy sequence of integers, what can you say? Can you say about the sequence? This has to be an almost constant sequence. The only possibility for x n to be an almost constant sequence. What does that means? That means there exists n greater than 0 such that all the terms beyond n, this n, are equal or constant. Now, how to give a textbook proof of this? How to give a textbook proof of this? Now, you have enough results and examples on sequences in general and Cauchy sequence in particular. Thus, I am leaving this question for you as a take home exercise. Okay. So, here we finish this particular module where we have discussed Cauchy sequences and some of their properties and some examples, and in the next module we are going to talk about monotone sequences. That will be another type of sequence.